Alright, so the next thing that I want to do is talk about kind of putting everything together that we've done to this point and how we can kind of further automate stuff using functions or just abstract kind of things using functions. So I want to try and do a couple things in this video. I want to write a function to approximate the area under a curve with some finite number of rectangles. I'd also like a function that returns that approximation with a plot of that, and also then finally a function that will return a side-by-side both approximate value given some n rectangles and an exact value with a plot. So let's get started. Normally we see our functions being used like this. I've used them just in line, kind of like this for the mathematical examples, but we've got a larger use of functions here where we can define it as any kind of input, do something to it, and return some kind of output. So to start, we have this little template here, which is a function called Integrator. It's going to take in some a, b, and f, where a is going to be a starting value, b is going to be the end value, f is some predefined function in terms of x. And right now I've got it set up to compute the width as b minus a and the height as f of b minus f of a, and just spit back what the change in height and the change in width are. So after I have that thing defined and I need to have a function defined in advance, I can go ahead and use it, and you see if I plug in start at 0 and 4, it's going to be a change of width of 4, but a change of height of 256, from 0 to 256 actually. Now this thing is saved as a function, okay? And just like before, if we want to look for help, we can use the question mark, and what we'll see is returned what I call a docstring here. So I just want to take this function and I want to extend it. I want to make sure that it will actually spit back an area approximation here. So we want to remember how we did that. First, we were finding the area of a rectangle, right? Where the width of a rectangle was given by b minus a over n, right? But so let's start with just n equals 10. And yeah, we need to, let's say that we're working from 2, b equals 2, and a equals 0. Okay? So then what we did was we found the width of each of our rectangles, right? And here we have our width is okay, it's 0.2. So then we found the height of our first rectangle by saying what is f of, go to that starting place and go over the width, and that's going to be the height of our first rectangle. So the area of it is going to be the width times f of a plus the width. If we wanted to find the area of the next rectangle, we would say the width times f of a plus 2 times the width, because we go over 2 widths now, and so on and so on and so on. So we really just need to kind of repeat this for as many as there are n's, right? So let's make a list of areas that are the width times f of a plus 2 times I for I in range n. And then, yeah, and if there's the different areas, it looks like actually I want to go from, because remember, this starts counting at 0, so this will give me the height at a, and we're building our rectangles at the right endpoint, so we want to go over 1. So I'm going to start at 1 and go to n plus 1. And there we go now. Okay, and then we just have to add that up. So sum the areas, and there's our area approximation. Okay, so we could print our approximation with however many rectangles is whatever we get, with n and areas. Actually, I'm sorry. We wanted the sum of these areas. Okay. So now what we can do is we can add that that piece back into. We can add this into our function. So if we just take this initial template here for the integrator and pay attention to what we just figured out, we're going to add in n for the number of rectangles. So we want to add a little text string here, and equals number of rectangles. We're going to return the approximate area of f with n rectangles. And yeah, after we found the width, right, what did we do? We found these areas. And we returned this statement. Okay, so now if we want to use the integrator, we'll see that we take in a start value, a stop value, a function, and a number of rectangles. So let's go from 0 to 2 with f with 10 rectangles, and there we go. We get our approximation. Great. All right, so the next thing that we want to do is we actually wanted to get this function to return a plot of it, right? So we're pretty close. The thing that we want to do is we actually want to then draw these rectangles at each of these widths and heights. So we're going to make a plot, and we're going to make a plot where x is going to start a little bit below what a is, and x is a little bit above what y is, right? So let's go back to like this example where we start with these values. Okay, so let's think about this. We want x to be a little bit, so we'll say from that lower number, we'll go back like a half, and same thing, b will go up a half, and we'll use however many n is times 100. All right, those will be our x's. Then we can plot this, right? X, f of x. Yeah, great. So there's our plot, and we can fill between x, f of x, where where are we going from? Where I is greater than a, and I is less than b, where I and x. Will that work? Yes, okay. Let's change that color. All right. Let's also add that horizontal line. Okay. Next thing that we want to do is we want to draw in the rectangles. So actually, I don't want this fill between yet, because what we're doing is we're saying it's an approximation. So what we can do is we can draw vertical lines from some y value to some other y value, but we need to draw a whole bunch of them. So if I look at this v-lines function, I give it some x value, and I say where the minimum y value and the maximum y value is. So for example, at 2, right, at x equals 2, I want to go from 0 to f of 2. So we can see that at 2, I want to go from 0 to f of 2, and then I get that vertical bar, okay? But I want to go through for each of my widths, right? So I'm going to use a for loop. So for I in range, and n is what's determining this. That's how many vertical lines I'm going to draw, right? I'm going to draw a vertical line. Let's see, where's my first vertical line going to be? I want it to go at a plus the width, and that's its x coordinate, and it's going to go at f of a plus the width, right? And I'm actually, again, I'm going to use that same structure times I, because I'm going to go through this loop, and let me go from 1 to n plus 1, and let's see what happens here. Oops, sorry, v-lines. Oh, and that goes from 0 to here. Okay, they were all at the same x coordinate there. I forgot to iterate through there. And okay, great. Now I'm going to actually shrink this thing down, because I don't think I need as much room on the left side there. Yeah, I want to be able to see those rectangles. Great. So the next piece that we have to build is we want to build the top of each of these, right? So I'm going to pop over a horizontal line here, similar plt dot h lines, and this is going to be, let's see, this goes from y and an x min and an x max, right? So my y is going to be this y, and my x min is going to be the a plus, let's see, where did we draw this? With, we want to go times I minus 1 to a plus width times I think. Let's see how this looks. Yeah, okay, great. And then we just need to add another set of vertical lines, right, to connect these, because really what we have are these rectangles that are going on each side. So we want one more. The way that I'll do it is just I'll do one more v-lines, and we'll just reel this back by one click. So times I minus 1 and times I minus 1. No, that didn't do it. Oh, because the height is going to be actually the same, right? It's at there we go. And now we have our representation for that. So we can just look. All we did was relied on the same stuff that we already had in that function. So we can just like copy and paste this and pop it right into the end of this dude here. So let's take our integrator function, and it's going to print that out, and then it's also going to give us, it should give us a plot like this. If we just literally take and pop this on the end of it, we need, All of our things indented. Sorry. This is awful. Okay. Let's try it again. Integrator from 0 to, let's say, 2, f with 10. Okay. Let's see. We just didn't get our plot returned. So I think that what I want to do is just add a couple more commands in here so that I make sure that I get that. Actually, what if I just still don't have my... Well, everything was going so well. This should just go from 0 to 2, but it's going from 0 to 20. So something's going on here with where I have my vertical lines being drawn. My width is computed wrong. It's b minus a over n. Forgot to change that. There we go. And we get it printed out. And we could change that. We could change this to from 1 to 5 with 30, or 3, let's say 3 rectangles. Sorry, I forgot my function. And yeah, great. Okay. So pretty neat. There's other approaches that we could have used to construct this geometry, including boxes, where we give the 4 coordinates of the endpoints, but I just thought that the V lines and H lines are a little bit more intuitive for that integrator function. So the last piece is that we want to return side-by-side plots of, let's see if this works still. Yeah, okay, great. What I want to do is I want to return side-by-side plots of the approximate and the actual value. So all we have to do to get the actual value is we convert this to sympy problem and use the integrator function, right? So let's write that in. I don't want to use x. I'll use xs for x symbolic, and we'll say that that's the symbol. XS, and I'm just so that I can use x, and because I already have x in here as part of this. So let me just, when I'm using it symbolically, I'll be using something called XS. Okay, so let's add that in here, like XS is going to be my symbol. And we are going to integrate. So let's call this thing exact, and we're just going to integrate f of xs from xs is a to b, right? And then what we can do is we've got that value here, and let's just make another, let's just add into our plots now. And so I'll make this a figure and increase the size. Let's say something like this. And then I will make this as a subplot. I'm going to have 1 row, 2 columns. This is the first of them. And I'll make one more subplot. That's 1 row, 2 columns. This is the second of those 2 plots. and this one will be the exact area. Let's see, where did I? And I'm just going to use that same kind of logic as I did before with this where loop, but now I don't actually have the values in here. Instead, I'm just comparing it to x is greater than a and x is less than b. And let's see what that does. Okay, great. I just need to add over a print statement that has the exact area. So let's see, where is that? This here, and let's say print our exact area is exact, and I need to have done that before, so let me actually move this to down here afterwards. Okay, there we go. And if we wanted to, we could add one more statement about the error. The error involved is what did we call this? All right, so not a very good approximation. But we can see that there is quite a bit of error involved here. Okay, so the exact error is going to be less than it, so yeah, we should have a negative difference. Great, so there's a big old walkthrough of a nice little function that allows us to kind of see the comparison between the exact and approximate areas. And really, this is more just to try and demonstrate how, now, if I ever wanted to solve a problem like this, I can just call this function. And the way that Python works is if I have this function saved as like a text file or something, okay, so I can just save that, and I'll call this thing, I'm going to name this integrals .py. So now I have this file here, integrals.py, and what I can do is in a notebook, make sure this is saved. What we're doing is I would say import integrals as, I don't know, let me just import integrals, okay? And then I'll say integrals dot, and you see that I have my integrator function there. And I can call it and say from 3 to 6 for f with 4 rectangles. Aha, and you see now NP is not defined. So I actually have to have my dependencies defined in here as well. So I want to do all my imports. PLT, import numpy as NP, import sympy sy. Okay, let's see about this now. I'll have to restart this. Let's see if that'll work. yeah, there we go. So now whenever you want to use it, you could do it like that. Okay? Nice little introduction to functions in Python.